Welcome to the Explainer. Today, we're cracking the code that's hidden inside every single barrel of crude oil. We're going to look right past that headline price you see on the news and uncover what really determines a barrel's true value to the entire global energy system.
You hear about oil prices all the time, but the number you're hearing is just for a benchmark, kind of like a reference point. In the real world, the price of any specific barrel can be wildly different. So what is it? What makes one barrel worth so much more than another?
Well, at a high level, the market uses these really simple labels, like light sweet and heavy sour. Light and sweet, that's the good stuff. It's less dense, low in sulfur, and way easier to refine, so it gets a premium price. Heavy and sour crudes are the exact opposite. They're difficult, costly to process, and always sold at a discount. But honestly, that's just scratching the surface. The true story of a barrel's worth is so much more complex. It's a story that's literally written in its molecular structure, a kind of chemical signature that dictates all of its potential and all of its problems. Okay, so to really understand a crude's value, we have to dig a lot deeper than the usual metrics like API gravity. It's time to look at the barrel's real blueprint. And the key to this whole thing is a tool called the True Boiling Point Curve, or TBP. You should really think of it as the crude's DNA. It's the refinery's map, showing them exactly what products are locked inside that barrel, and in what amounts, before they even start to process it. And this slide right here shows you exactly why API gravity isn't the whole story. I mean, look at this. Both of these crudes have the same 35-degree API, but their potential yields are completely different. If you're a refinery that needs to make a lot of diesel, crude B is an absolute gold mine. Same density, but a world of difference in economic potential. And this is how that blueprint actually plays out in the real world. Inside the refinery's distillation column, heat separates the crude into layers. You get the lightest, most valuable stuff like naphtha way up at the top, and the heavy, problematic residue sinks all the way to the bottom. Each and every layer has a different purpose and a different value. But here's the thing. A barrel's potential isn't just about the good stuff you can get out of it. It's also about the hidden penalties a refinery has to pay just to process it. And these penalties are what truly define a crude as difficult, and they can absolutely crush its value. There are basically three main culprits that create major headaches and big costs for refiners. We're talking sulfur, acidity, and metals. And believe me, these aren't just minor little impurities. They are active agents of destruction and expense inside a refinery. First up, you've got sulfur. Now, to meet clean fuel standards, all that sulfur has to come out, period. But the process for removing it consumes massive amounts of incredibly expensive hydrogen. So a high-sulfur crude acts like a thief, stealing one of the refinery's most critical and costly resources. It's like an unavoidable tax on every single sour barrel. Next up is something called the total acid number, or TAN. This measures naphthenic acids in the crude. And when these acids get hot, they become super corrosive. I mean, they will literally eat away at the refinery's steel pipes, furnaces, and towers from the inside out. Processing a high-tan crude requires expensive, specialized metals, which is why most refineries just can't handle it. And finally, we have metals. We're mostly talking about vanadium and nickel here. These are concentrated in the heaviest parts of the barrel, and they are pure poison to the expensive catalysts that are essential for turning heavy oils into valuable gasoline and diesel. They just clog up the catalysts, kill their effectiveness, and force the refinery into costly, frequent replacements. So the crucial point here is that all these penalties create what the industry calls a quality ladder. At the very top rung, you have the light, sweet crudes, super easy to process, very few penalties. And way, way down at the bottom rung, that's where you find the heavy, high-metal, high-acid barrels that only the most sophisticated refineries in the world can even touch. And they'll only do it if they can get a steep, steep discount. Okay, so let's take a quick tour of the barrel and see how this all comes together in the final products that actually power our world. We'll go from the top to the economic core and all the way down to that problematic bottom. Right at the top, you've got the light, volatile stuff, like naphtha. This is a really crucial feedstock, and it creates this constant tug-of-war inside the refinery. Should they use it to make high-octane gasoline for cars, or should they divert it to a steam cracker to make the building blocks for all our plastics? Its fate depends entirely on which market is willing to pay more. In the middle, you find the economic core of the barrel, the middle distillates. This is where we get the diesel and jet fuel that power global commerce. I'm talking about the trucks on our highways, the container ships on our oceans, and the planes in our skies. The value of this section alone can often determine the entire profitability of the refinery. And then we get to the bottom, the residue. This is the thick, difficult, tar-like gunk that's left over after everything else is boiled off. And it's where the highest concentration of all those hidden penalties, the sulfur, the metals, the acids, ends up. It is, without a doubt, a refinery's biggest challenge. So what can a refinery even do with this stuff? Well, their level of sophistication really comes down to how they handle it. They can either crack it into a solid fuel called petcoke, they can try to upgrade it by pumping in a ton of that expensive hydrogen, or they can just sell it off as cheap fuel oil. And believe me, each one of those choices has huge economic consequences. So how does a refinery put all these pieces together? How do they weigh the good, the bad, and the ugly inside every barrel to figure out what it's truly worth to them? This quote really just nails it. A refinery's ability to handle that nasty residue, that is what separates the winners from the losers in this business. It's the ultimate test of their sophistication. Ultimately, it all comes down to one final complex calculation. Refiners use these powerful computer models that run what's called a value and use analysis. The model takes the TBP blueprint, that's the potential value of all of the products, and then it subtracts the total costs of all those hidden penalties. What's left over is a precise value for that specific barrel in that specific refinery on that specific day. That is its true worth. And this leaves us with a final thought. As our energy needs keep changing, with the rise of electric vehicles, but the persistence of air travel, which part of the barrel is going to define its future value? Will it be the volatile top for plastics, the economic core for jets and ships, or will it be the refinery's ability to eliminate that problematic bottom altogether? That is the code the entire industry is trying to crack right now.